Hey guys, welcome back. Today we're going to look at how to use reference angles to help us find trig ratios of angles that go through different points on a coordinate plane, and also angles that pass through different points on the outside of a circle. So first off, just what is a reference triangle? A reference triangle is a right triangle that's drawn from the point on the terminal side of an angle connected back to the x-axis. It helps us turn any angle into a right triangle so that once you have that right triangle, you can find the sine, cosine, tangent, and the reciprocals if needed. So looking at the first one, it asks us to find the sine, cosine, and tangent, so just the three OG trig ratios for angle theta that passes through the following point. So first thing I'm going to do is put my vertex at the origin so I can get this angle in standard position. Its initial ray will be on the positive x-axis, and then the terminal ray is going to be the one that passes through the point -3, -4. -3, -4 is right here. Okay, so there is the actual angle. That whole entire thing is the angle, but we want to connect the point here back to the x-axis to create a reference triangle and a reference angle. So I'm going to take the point -3, 4, connect it back to the x-axis, and you can see how that creates a little triangle here. So in this triangle, this little guy right here is the actual reference angle. Notice the reference angle is an acute angle. And you can see the right angle right here. Across from that would then be your hypotenuse. So from here, because this is in a coordinate plane, we actually measure these with negatives. So instead of just saying that this has a distance of 3 and a distance of 4, we actually use their negative numbers, -3, -4. And then in order to find my trig ratios, I am going to need to find that third side, which you might know, it is a Pythagorean triple, but if you don't, remember you can also find it by doing a little a squared plus b squared equals c squared. And that gives you 9 plus 16 equals c squared, which means c squared is 25. So c is 5, which again, you probably already knew that. 3, 4, and 5 always go together. So from here, we can now find our trig ratios. So I'm going to set up my sine of the angle. And when again, we're using this little reference angle as our angle. Sine of the angle. Remember, sine's trig ratio is opposite over hypotenuse. Opposite over hypotenuse. So from this angle, the opposite side would be -4, and the hypotenuse would be 5. And then we have cosine of the angle. Cosine's trig ratio, remember, is cosine is adjacent over hypotenuse. So from this angle, the adjacent side would be -3, and the hypotenuse again is still 5. And then also tangent of the angle. Tangent is opposite over adjacent. So using the reference angle is what we're referring from. The opposite side would be -4. The adjacent side would be -3, which would reduce to 4/3. Okay, similar for the next one. The next one, though, is passing through the point -5, 12. Notice I didn't put any lines on this one, only just because I would need a large coordinate plane to get to 12. So I'm just going to kind of approximate where 12 would be. We are still going to draw this angle in standard position, so it has its vertex at the origin. Its initial ray is on the positive x-axis, and then it needs to pass through the point -5, 12. So -5, 12 would be left 5 and up 12, which I'm just going to approximate as right there. Drawing in my angle. So the actual angle is right here, but we're not going to be able to find our trig ratios if we don't have a right triangle. So we're going to take where it went through that point at -5, +12, and we're going to connect it back to the x-axis to create our reference triangle. Our reference triangle, again, to get to this point here, we went left 5 and up 12. Okay, so the actual reference angle is the little acute angle that's right here. Reference angle. Okay, and then from here, we need to find the third side of our right triangle. This is another Pythagorean triple, so some of you guys might already know what the hypotenuse measures. If you don't remember, you can do a little a squared plus b squared equals c squared. That would become 25 plus 144 equals c squared. So c squared equals 169, which means c is 13. So that missing side on the right triangle is 13. And then from here, we can find our three OG trig ratios. So we'll have sine of the angle, which again, we're using this reference angle right here is what we're referring from. Sine of the angle would be opposite over hypotenuse. Cosine of the angle would be the adjacent side, which remember we do use negatives when it's in a coordinate plane, adjacent over hypotenuse. And then our tangent of the angle would be the opposite over adjacent. So looking from this angle, the opposite would be 12 and the adjacent would be -5. All right, looking next at just how to calculate a reference angle. We have, what are 4 different angles that would have a reference angle of 20 degrees? So in the last ones, we didn't actually measure what the reference angle was. We could if we wanted to. We would have to just use an inverse trig function to find the angle measure. But there's lots of different angles that would have reference angles of 20 degrees. First off, if you end up with a angle that's about right here, your reference angle would be this little 20-degree angle here. And then the actual angle itself that would have a reference angle of 20 degrees would be this angle, which remember the whole entire thing is 180. So if we take away 20 from that, this would be a 160-degree angle that has a reference angle of 20. Another one, if we draw it in standard position, say the terminal ray ended up in the third quadrant. So say this was the 20-degree angle right here. That's our 20-degree reference angle. Well, the actual angle that would produce a 20-degree reference angle comes all the way over here and continues down. So that would be 180 degrees plus 20 degrees more, which would be 200 degrees. Let's see, if it was in quadrant 4, let's see, initial ray, quadrant 4 would go all the way around, and then you'd end up with some sort of little 20-degree angle right here. So say this was 20 degrees. Again, the actual angle itself is the one that went all the way around. So since entirely around a circle is 360 degrees, 20 degrees less than that would be, this is a 340-degree angle that has a reference angle of 20 degrees. And then you also have reference angles even for angles that are above 360 degrees. So say we went all the way around plus a little more. And then we'd have this little angle right here, not drawn to scale, obviously that does not look like 20 degrees. This little angle here would be a reference angle of 20 degrees, but that initially was not a 20-degree angle. If we went all the way around plus 20 degrees more, that would actually be a 380-degree angle that would have a reference angle of 20 degrees. The next one, we are given a angle in radians, which we have learned how to convert radians to degrees. In what quadrant would the terminal ray of an angle in standard position that measures 8 pi over 5 lie? And what would be its reference angle? Let me scoot this down. So last time, was it last time? Last time, maybe one more lesson before that, we learned to convert an angle from radians into degrees. 8 pi over 5. We need this pi to be able to cancel. So we know it's always involving something with a 180 and a pi. It's just sometimes hard to remember which one goes on top, which one goes on bottom. But in order to convert this into degrees, we need this pi to cancel, which means the pi is going to go on the bottom and the 180 is going to go on the top. And then I'm going to do a little bit of reducing. I see this 5 would reduce with this 180 here. Both of them are divisible by 5. And that would give me 36 here. And now if I do top times top, bottom times bottom, I get 288 degrees. So this is the angle that I want to actually draw so that I can figure out what quadrant the terminal ray is in, and then also what its reference angle would be. All right, so 288 degrees. So I know right angle, that's 90. Straight angle, that is 180. If I went one more quadrant down, this is 270. So 288 is just a little past there. So all the way around is 288 degrees. So to answer the question says, in what quadrant is the terminal ray? Well, we know it's in quadrant 1, 2, 3, 4. That is quadrant 4. I'm going to use Roman numerals. Usually we use Roman numerals for quadrants, but if you just write 4, that's okay also. And then figuring out the reference angle. The reference angle, remember, is the one that's connected back to the x-axis. So this guy here would be the reference angle. So that would be, if we went all the way around, that would be 360. So I need to actually do 360 minus 288 to figure out what that little angle is. What is 360 minus 288? 72 degrees. 72 degree reference angle. Remember, a reference angle should always be an acute angle, so that's kind of how you can tell, like, did I do it right? If it's an acute angle or not. Just reminding you about some special right triangle stuff that you learned in geometry from last year. You did learn about how to label the size of triangles if it's a 45, 45, 90 triangle, and then how to label it if it's a 30, 60, 90 triangle. So I'm going to remind you how the sides are related on each of these, and then we're going to use one of those to help us solve a question on the right-hand side. So on a 45, 45, 90, because two of your angles measure the same, you'll have a 45 degree here, a 45 degree here, and then your 90 in the corner. The sides that are across from those two should also be the same, but we don't necessarily know what they are. They could be any of the two same numbers, so I'm just going to mark them with x, x. And then the way the hypotenuse is related, it's whatever this side length was times the square root of 2. So like if each of these are 3, your hypotenuse would be 3 squared root of 2. But since my sides are measured x, my hypotenuse is just going to be x square root of 2. And then looking at a 30, 60, 90, so I'm going to put my smallest angle at the top, make this the 30 degrees, make this the 60 degrees, and then our 90 degree in the corner. So the smallest side and the hypotenuse are related in that the smallest side on a 30, 60, 90 is half of the length of the hypotenuse. So that means if I called my smallest leg x, then this should be half of what my hypotenuse is. So my hypotenuse should be 2x. And then the other leg is whatever the shortest leg is times the square root of 3. So like if this measured 4, this would be 4 square root of 3. If this measured 5, this would be 5 square root of 3. But this measures x for us, so we're going to call this x square root of 3. All right, now that we've reviewed that, we're going to find the value of sine, cosine, and tangent for a 135 degree angle. So first thing I'm going to do is just draw that so I can see how long or how big the reference angle would be. So starting by drawing it in standard position, vertex at the origin, initial ray on the positive x-axis. And remember, a completely straight angle would be 180 degrees. So 135 is actually a halfway between the 90 and 180, just like that. So here's my 135 degree angle, but I need to actually know my reference angle in order to do my sine, cosine, tangent. So my reference angle would be the acute angle that's found by connecting this angle down to the x-axis. So right here is my reference triangle. And then this little guy here is my actual reference angle. And if you do 180 minus this 135 degrees, you'll find out that that reference angle is actually a 45 degree angle. Which if it's a 45 degree angle, then that means that this triangle is actually a 45, 45, 90 triangle. Now what we call these sides because I wasn't given an actual point that they pass through, I can't really say like, oh, well, I guess I could say, I could actually call these any numbers. I could call this -2, +2. I could call this -3, +3. It doesn't matter. The final answers for our sine, cosine, and tangent will reduce to the same. So I'm going to do that. I'm just going to call it some random number. Where's my black pen? Okay, so I'm going to say, well, let's say maybe this length was -2. So then this one would be the same number, but since we're going up, it can't be negative. So I'm going to call that +2. And then if you look at how the hypotenuse was related to those two lengths that are the same, the hypotenuse should be the side length times the square root of 2. So we're going to call this 2 square root of 2 for our right triangle. And then once we have that, we can find our sine, cosine, tangent because we know all three sides on the right triangle. So starting with sine of the angle, and again we're using the reference angle that's 45 degrees. Sine would be the opposite over hypotenuse. So 2 over 2 square root of 2. We'll get a little reducing. It'll become 1 over square root of 2, which remember you can rationalize that by multiplying by square root of 2. Oops, I forgot to write the 2. Leaving us with square root of 2 over 2. And then cosine of the angle. Cosine is the adjacent over hypotenuse. So -2 over 2 square root of 2, which is going to reduce very similar to how the sine did. The only thing difference is because it was negative with that adjacent side, your final answer will be negative. And then the tangent of the angle would be opposite over adjacent. So that would be 2 over -2, which would then just reduce to -1. All right, moving on. Backside, what do we got? What if the point is on a circle? Okay. I'm going to show you basically what we just did, if the point is on a circle, how to find the sine and cosine. And then I'll show you a trick that you can use so that we don't have to do these big long calculations every time it's on a circle. It says, consider angle B. I believe that's the Greek letter beta. Let me see. Consider angle B. What is the value of sine of B and cosine of B if point A had each of the following pairs of coordinates? And I just did literally just one point. There were several examples I thought about doing, but then I changed it up. Okay, so we've got a coordinate that is 12 over 13, 5 over 13. And it says it goes through point A, which would be right here. Here's the angle. I did Google it. This is the letter beta. So sine of beta, cosine of beta. So to get to this point right here, which is 12/13 over 5/13, we'd have to go right 12/13 and up 5/13, which does create like a little triangle that we can use. So that triangle, we had to go right 12/13 and up 5/13. So in order to find our our 2 trig ratios, this one's not asking for all 6 of them. First thing we're going to need to do is find the length of the hypotenuse, that third side. Again, I'm showing you the hard way first, and then I'll show you the trick. So I'm going to do a little a squared plus b squared equals c squared, where a and b are just the legs of the triangle. So we'll have 12/13 squared plus 5/13 squared equals c squared. So this would be 144 over 169 plus 25 over 169 equals c squared. When you add fractions with the same denominator, remember you only add the numerators. So those two numerators would add to 169 over 169, which means c squared is 1, which means the hypotenuse is also just 1. Okay, so now that we know the hypotenuse, we can do sine of beta and cosine of beta. Okay, using the little beta angle as what we're referring from for what is opposite and what is adjacent. So starting with the sine of beta, Sine of beta would be opposite over hypotenuse, which is just 5 over 13 over 1, which would just be 5 over 13. And then cosine of beta would be the adjacent side over the hypotenuse, 12/13 over 1, which would just be 12/13. And is anyone looking at this going, what the heck, those are just the numbers we started with in the point? Yes, that's what you should be thinking. You should be looking at those going, oh shoot, those are just the same numbers from the points. Specifically, the sine was just the y value from the point, and the cosine was just the x value from the point. And we're gonna look more in depth with that with our little definition right here. In summary, if the radius of your circle is 1, which ours was a 1, you could actually see it right there, there it is, radius of the circle, then those two numbers that you're given for the xy coordinate are going to always be the cosine and the sine. If the radius changes and it's on a circle, all you're gonna do is multiply the sine and the cosine by the radius. So radius times the cosine of the angle, radius times the sine of the angle. Quick little shorthand so we don't have to always sit here and do a squared plus b squared equals c squared. We can just say, oh, well, that's the cosine, that's the sine. Looking at the next section, it says, given the radius of the circle and the measure of angle alpha, we're going full Greek today, determine the coordinates of the point on the circle where the terminal ray intersects the circle, round to 2 decimal places if needed. So you will need your calculator for this, for determining the coordinates of the point on the circle where the terminal ray intersects the circle, and we don't even have to draw this out, round to 2 places if needed. So on the first one, we're given a radius of 2, and we're given alpha, which is the angle measure, is 4 radians. Now, since this is in radians, your calculator actually needs to be in radians, which is rare for us. Usually I'm squawking at you to turn it to degrees. So when you press mode on your calculator, you're gonna, where's radians? Right here. Mine is in radians. If yours is in degrees, switch it back. Anytime you clear the memory on your calculator, it defaults back to radians anyways. So for the first one, to find the coordinates of the terminal ray, we're gonna say, well, it's just 2 times cosine of the angle, which is 4 radians. That's the first one. And then our radius again, 2 times sine of the angle, which is again 4 radians. So my first one, to do the calculation, I'm going to do 2 times cosine of 4 radians, which my calculator is in radians. So the first number would be negative 1 point, what did I say to round to? 2 decimal places, negative 1.31. And then my second one, 2 times the sine of 4 radians, would be negative 1.51. And that would be the ordered pair if you were to graph this angle on a coordinate plane. It would go through the point negative 1.3-ish, negative 1.5-ish. For the second one, similar situation. On this one, the radius is 3, and the angle is negative 7 pi over 10 radians. So again, make sure calculator needs to be in radians when we're given it in radians. So again, what we're doing is this one right here. The ordered pair is radius times cosine of the angle, comma, radius times sine of the angle. So we're gonna have our radius times cosine of the angle, which is negative 7 pi over 10, comma, and then the y value of the point would be radius times the sine of the angle, negative 7 pi over 10. And then we'll get those calculated so that we see our x and our y. So the first one, I'm going to have 3 times the cosine of, I'm going to do a little fraction, negative 7 pi over 10. So the x value of the ordered pair would be negative 1.76. And then for the y value, we'll do 3 times the sine of negative 7 pi over 10. Oh, I typed it different on both. Well, you can see, now there's 2 different ways to type it. And we get negative 2.4, and then this would turn into a 3 because the 7 would bump the 2 up. All right, there we go, an x and a y value. So if we were to plot this, it would go through the point negative 1.76, negative 2.43. Let's read the next one. Suppose a circle centered at the origin has a radius of 5 units. Determine the coordinates of the point on the circle where the terminal rate of angle negative 11 pi over 6 intersects the circle. Round to 2 decimal places if needed. I'm going to assume that this is in radians. Usually anytime there's a pi like that, it is in radians. So again, I'm going to use the same formula that I had up top. The coordinate is going to be radius times cosine of the angle times radius, or comma, radius times the sine of the angle. Okay, and both of these, my radius is 5, so I'm going to have 5 times cosine of negative 11 pi over 6. And then my y value of my coordinate would be 5 times the sine of negative 11 pi over 6. And then we'll get those calculated. First one, 5 times the cosine of negative 11 pi over 6. So the x value of the ordered pair would be 4.33. And then the y value, 5 times the sine of negative 11 pi over 6. And oh, a nice number. No need to round, 2.5. And that is our ordered pair. Last question of the day does come from AP Classroom. Let's read it. I'll move my paper. Stuck. Okay, so we're given a graph. All right, just kind of looking at the graph here. Looks like the circle goes through the point 10, 0, which means it would have a radius of 10. In the xy plane, a line segment has one end point at the origin and the other endpoint on a circle with a radius of 10. The line segment forms a 140-degree angle with the positive x-axis. What are the coordinates of the point where the line segment and the circle intersect? Okay. We're going to do literally just like we did on the last ones. This one is in degrees though, so you'll need to make sure you put your calculator in degrees for this one. Okay, so I'm going to go to mode. I'm going to arrow down here to radians, switch it over to degrees. Okay. And I know you might be thinking you need to use a reference angle on this one, but you actually don't have to. We're not trying to calculate our trig ratios. Like, we're not trying to say, you know, what is the sine of this? What is the cosine of this? We're just trying to find the ordered pair that it's going to out here. So we're going to use our little formula that we wrote down earlier. We've got our radius times the cosine of the angle, and then the second one is radius times sine of the angle, and it is a 140-degree angle. So we'll have 10 times cosine of 140 and 10 times the sine of 140. Excuse me. Again, calculator does need to be in degrees for this one. Let's see. 10 times cosine of 140. So the first number should be negative 7.66, which I guess, oh no, close enough. Negative 7.66, comma, and that is the only one that has negative 7.66 up here. None others have that. I am going to verify real quick just the sine value is correct. 10 times the sine of the angle, which was 140. 6.43-ish. There we go. All right, it does look like it is answer A. Looks like we probably could not have narrowed down. I thought for a second like maybe we could narrow down, like because it's in quadrant 2 it needs to be a negative and a positive, but they're all negatives and then positive. AP Classroom, they're not trying to trick us, or they are trying to trick us. All right, thanks for learning today, guys.